All right. Induced current. Induced current. All right. Um, Lenz's law, and let me warn you, he's a little bit of a yapper. Okay, he says the induced current, okay, will always, okay, have a direction such that, okay, the induced current, okay, opposes, okay, whatever mechanism charge or changes the flux. It's a lot of words just to introduce yet another right-hand rule that you need to know. Yeah, I know. There's like 5 right-hand rules for this unit, okay? In general, if the flux is increasing, okay, then you have to use your left hand, okay? If the flux is decreasing, okay, you would have to use your right hand, okay? And in general, right, when you're, so this is another grasp rule, okay, where your fingers curl around and your thumb points. So your thumb, okay, is in the direction of the B field, okay, through loop, okay, and then your fingers curl in direction of induced current, okay. So your fingers will curl in the direction of the induced current. Your thumb points in the direction of B field through the loop. Very, very similar to the right-hand rule. I believe is the one we learned for us, like a solenoid, right? Very similar to that, except now you have to consider is if the flux is increasing, you use your left hand. If it's decreasing, you use your right hand. Okay. So here's some examples. The north pole of a magnet moves towards a wire loop, okay, you're going to know, right? You should know that if we're talking about the north pole of the magnet, right, then the magnetic field produced by the magnet, okay, if we're talking about the north pole, the magnetic field goes away from the north pole, right? So through the loop, these magnetic field lines are going to point down, okay, and the velocity is moving towards it. So the magnetic flux is going down, okay? It's the same as the B field direction. And is it increasing or decreasing? Well, the magnet's getting closer, so you can think of there's a bunch of little magnetic field lines coming out from the North Pole, and as we get closer, the loop is catching more of those. So it's actually increasing. Okay? So then we're doing the dots to show the induced current's magnetic field, and then we're also showing where the induced current's coming from, right? So the magnetic field is going down and it's increasing, so I'm going to use my left hand, okay? The magnetic field goes down and it's increasing, so I'd go like that, and you'll notice that my fingers go into the page on the right side and out of the page on the left side, right? So I'll draw that here, into the page on the left side, out of the page on the right, and the magnetic field is circling, okay, like that, okay? So then we got to use our other right-hand rule, the one that we learned in like the first couple of sections, right? For like the coil, okay, current is going around this way. So what direction is the magnetic field going? It would have to go up, okay? Now, I want you to envision this ring like it's a magnet, okay? If the magnetic field lines are leaving the top, this is basically a bar, no different than a bar magnet with its north pole going up and its south pole going down, right? So what's happening is you have this is like a bar magnet, north pole going up, south pole going down. Wait, the two north poles are pointed towards each other. So what's going to happen? They're going to feel a force opposing each other, okay? That's the magnetic force they're going to feel because they're basically, right, the north poles are together, so they're basically pushing each other away, okay? Okay, the north pole of a magnet moves away from the wire loop, okay? So now what's happening is instead the wire is same orientation, but it's moving downwards now. It's past the loop, okay? It's moving away from it. So we would notice that this is the south pole, right? So the magnetic field lines are attracted to it. Okay, so magnetic flux is going down still, but it's now decreasing. Why? Because this is moving away, so so it's actually not able to catch as many of the magnetic field lines because it's moving away, right? So the induced current, it's decreasing and going down, so I'm going to use my right hand, okay? Right hand, thumb points down, it goes into the page on the left and out of page on the right, okay? Okay. Then to figure out the direction, okay, so then we use the legit right hand rule, okay? Curl and it goes down, okay? So if we were to imagine this as being a bar magnet, it would be a bar magnet where the north pole is down and the south pole is up, okay? So wait, then your north pole and your south pole are facing each other, which means that they are attracted to each other. So it would feel a force, the ring would feel a force going down, and the magnet would feel a force going up, okay? Does that make sense? Okay, the south pole of the magnet moves towards the wire loop. This is the same case as above, but flipped, okay? We feel the field lines going towards the south pole, okay? So the magnetic flux is upwards, and the field is increasing because it's getting closer, okay? Okay. It's increasing, so we use our left hand, okay? So thumb goes up, and you notice it goes into the page on the left side, out of the page on the right side, so it circles around like that, okay? And then in the middle part right here, okay, you should see, again, we would use our other right hand rule, so like that, and my thumb is pointing down, okay? So the force so the magnetic field lines are going to go down. So this is like a magnet in where the north pole is down and the south pole is up, right? So then these two would be repulsed from each other because it's the same poles, okay? Okay. All right. That's too far. Okay. You would do the same thing for this example right here. Okay. Oh gosh, why is it crooked? There we go. Okay. The south pole of the magnet moves away from the wire loop, so this is again the same example, but the magnet is flipped now. Okay. The north pole, it shoots the field lines out of it, right? So they're going away from it. Okay. And then so the magnetic flux is upwards and it is decreasing. Okay. And then up here, you would notice that, of course, you know, the magnetic field is going upwards, right? And it's decreasing, so you use your right hand, and it goes into the page on the right side and out of the page on the left. Okay. Oh, wait, sorry, I got those symbols mixed up there. Should be into the page on the right, and then out of the page on the left. Okay, I'm just shading in the whole dot so you get the point. Okay, because I kind of messed up a little bit there. Okay, so the current is going to circle this way. Okay, and then you should notice again if it's circling that way, right hand rule, then the created field is going to go up. Okay. And what will happen here is that then you notice again, this is like a bar magnet where it has the north pole going up and south pole going down. So they should be attracted to each other. Okay. Okay. So there's that. Okay. Switch is just closed so that so now this is a new example where we have two rings of charge, right? So you notice that there's a little switch. It's kind of hard to see right there. There's a little switch right there. We've just closed it. So what that means is that this loop is now kind of charging up, right? So what's happening is as as the field is increasing, right? What's happening is that it currently has, right? This is the positive terminal of the battery. Here's the negative. So what's happening is the current is going around this way, and then it's going to circle around this way and this way, okay? And then come back to the battery this way, okay? If it's going that way, okay, then we use our right hand rule to see that the magnetic field is going to the right. So that's how it's going to look. That's the magnetic field from the right loop. Okay, so the magnetic flux in the left loop is rightward, and it is increasing. How do we know it's increasing? Because this is charging up. So as the current increases, the magnetic field should also increase too. Okay. So then what we can do is we have the magnetic field going to the right. It's increasing, so we need to use our left hand. Okay. Our magnetic field goes to the right. And we should see that what's going to happen is it's going to go into the page on the top, out of the page at the bottom. So you would see that this is going to go basically the opposite direction. Okay. And if we do that, then we can use our right hand rule and see that the magnetic field that's being produced is going to the left. Okay, so this is like a bar magnet in where north is to the left and south is to the right. For the other one, right, for the other loop, this is like a bar magnet in where north is to the right and south is to the left. So you see that they are repulsed from each other. Okay. Okay. Now what's happened is we've now opened the switch, and it says the current in the right loop is beginning to increase. It should actually be decrease, right? Because it's discharging. And so what's happening as there's still some current in there, but it's discharging, right? We would see again, it's still flowing in the same direction, okay? And the magnetic field is still going in the same direction because the current's going in the same direction, okay? So it's still to the right, but it's decreasing because our current is decreasing, right? So then what we would do is in the next image, right? This is going there. We would use our right hand instead. Okay, our B field's going to the right. So it would actually have the same direction as the right loop now. And the magnetic field produced from it would also go to the right. Okay. So now what's happening is this is like a bar magnet in where north is to the right and south is to the left, and then the orientation doesn't change for the other one, so these two would actually be attracted to each other now. Okay, they would actually be attracted to each other now. Okay. This example right here, a loop of wire is set in a magnetic field B, considering the following. Magnetic field points out of the page and is increasing. Okay, well, first off, I need to figure out which hand rule would I need to use for each one. Okay. So for the first one, right, if it's increasing, I'm going to use my left hand. Okay. If it's increasing, left hand. For number 2, it's decreasing. So I would use my right hand. And then decreasing, I would also use my right hand. Okay. So I'm going to use the left hand examples first. If it points out of the page and is increasing, okay, out of the page, increasing, so left hand, then it's going which way? It looks like it's going clockwise, right? Okay. What about the other one? Into the page and is increasing. So thumb down, and it looks like it's going counterclockwise. Okay. What about for my right hand? My right hand is out of the page. Okay. That's going to go counterclockwise. Okay. That should be 2. Sorry, not 3. Okay. Or sorry, counterclockwise. That would be in this spot right here. And then down, my thumb goes down into the page. You'll see that it's going clockwise. So then that would be 4. Okay. So 1 and 4, and then 3 and 2. Okay. Okay. A loop of wire in the plane of the page lies halfway in a magnetic field perpendicular to the page. In which direction must the loop move in order to create the current with the direction indicated? So if we want it to move, right, we want the current to be clockwise. Okay, so then we can test it, right? So the magnetic field's out of the page. So we want to test it with our hands now. Which one will give us this? So thumbs up on left hand or right hand will give us clockwise, right? That gives us counterclockwise, okay? But this gives us clockwise. So we need an increasing flux, okay? And in order to get increasing flux, we want to shift the circle into the page, okay? We want to, or not into the page, into the magnetic field. Okay. Okay. We want to shift it into the magnetic field, so we need to move the loop to the right. Current is counterclockwise. Okay, into the page. That gives us clockwise, right hand. Left hand gives us counterclockwise, so we need an increasing flux. So let's move that up. Okay. Do you see what I'm doing? It's pretty Pretty straightforward, right? Another thing you can do here for process of elimination is that understand that moving this directly up or down isn't going to do anything, right? It's not going to do anything because if we're pretending like this field is like infinitely long, right? Upwards, right? Moving it up isn't going to do anything until, of course, we move it out of the field eventually. But that's too much, right? We can either move it left or right to move it. So you can automatically knock out up and down. Here you could knock out left and right because again, that's not going to do anything. You can knock out up and down here because that's not going to do anything. Left and right isn't going to do anything. Up and down is not going to do anything. Okay, we're just taking out the choices that don't matter to us right now. Okay, current is clockwise. Okay, if I'm doing decreasing, this is counterclockwise, then increasing would be clockwise. So I would use my left hand, so we need an increasing amount, so it would need to go into the field, okay? Counterclockwise current, okay, out of the field, right? This gives us clockwise, so decreasing gives us clockwise, or decreasing gives us clockwise. Increasing is going to give us a counterclockwise current, okay? So we would need to move it into the field, which would be going down, okay? None of these have been decreasing yet. That's crazy. For current to be clockwise, right? Okay, into the page. Okay, right gives us clockwise, so we would need to be decreasing, so we need to move it out of the field, okay? Okay, and then here's another example. The last example for this section is a loop of wire and a long cable both lie in the same, in the plane of the page, okay? The cable carries a current I. Determine whether the current induced in the loop is clockwise, counterclockwise, or zero. Okay, so this is kind of a two-step example here where you have to figure out the current from each of the wires. So you would use your grasp rule for each of the wires, okay? This is going to go into the page on this side and then out of the page on the left, okay? This is going to go into the page on the left side and out of the page on the right, okay? Into the page on the left, out of the page on the right, okay? Into the page on the left, or sorry, on the right, out of the page on the left, okay? This one is going to be right here. It would be out of the page on the top part and into the page below. Wire moves up. It goes into the page above, out of the page below, okay? Loop moves down, again, into the page, or sorry, it should be like that, into the page above, out of the page below. And then this one again, it would be into the page below, out of the page above, okay? Okay, then we've already figured out our E field direction, or we've already figured out, sorry, our B field directions from the wires, right? Okay, it's going into the page, okay? For current to increase, right? Then what's going to happen is it's going into the page. So current increases, that means flux is increasing, okay? So left hand, B field into the page, it's going to go around this way, which would be counterclockwise, right? Okay. If I is decreasing, then we would use our right hand because flux is decreasing, okay? And it would be, looks like it's also going to be counterclockwise, okay? If the current's constant, then nothing's changing here. So we would have no change, or there would be no change in flux there, okay? Or there would be no induced current. Loop moves to the left, okay? If we move it to the left, it's getting further away, so it's decreasing, okay? The B field strength is decreasing, so we would use our right hand, okay? And that gives us a counterclockwise, okay? If the loop is moving to the right, then nothing is changing, right? Because it's not moving up or down any. It's not moving at all, okay? The loop moves up. That means it's getting closer to the wire, so increasing B field. So we use our left hand. That gives us a clockwise induced current. If the loop is moving down, again, B field is getting stronger, so it's increasing. So we would use our left hand into the page. That looks like it's going to be counterclockwise. Okay, and finally, if the cable moves up, oh, this is important, the cable's moving up this time, not the loop. If the cable moves up, then the B field is decreasing, which means flux is decreasing. So right hand, boom, into the page, and it would go, that would be clockwise, right? Okay, well, there you go. That's all for that section. Okay, have fun. Girl boss it up.